Hi everyone, I'm Gennaro Laudato and I'm presenting this work on behalf of the research group composed of the State Lab from the University of Molise, Italy, where I belong, and the Regional Sanitary Company of Molise. We are living in the era of wearable devices, which are important components of human health for the prevention of disease or pathological conditions. Well, the use of Internet of Medical Things systems for remote health monitoring is playing a pivotal role in improving both the effectiveness of medical devices and the accessibility to medical services. Remote health monitoring refers to a process where the patient's health is continuously checked, thus allow the identification and prevention of disease. A common pathological condition is congestive heart failure, with around 26 million adults diagnosed with the disease worldwide in 2014. Therefore, much effort was undertaken by the scientific community to aim at automatically identify congestive heart failure. Most of the work proposed a detector of CHF that provides a binary classification of a signal in congestive heart failure and normal sinus rhythm. Only a minor part of the scientific community has modeled the CHF detection problem as a multi-class prediction. In such cases, three classes are typically used: CHF, normal sinus rhythm, and no CHF with the meaning of pathological but not heart failure rhythm. The main drawbacks of such literature approaches is that they provide only binary classification or that they depend on other safety-critical algorithms to obtain the ECG segmentation. To mitigate such limitation, we present Harper, a novel tool where its name comes from its description, the detector of congestive heart failure episodes for medical support. Harper is an automatic method to detect congestive heart failure in a single lead digital ECG. Harper is a near real-time approach capable of multi-class identification of a given windowed ECG signal in congestive heart failure, normal sinus rhythm, and no congestive heart failure, which means pathological rhythm but different from heart failure. In our perspective, the main contribution of this work are the following. We first introduce Harper, which is a reliable and independent detector because it is capable of providing a multi-class identification instead of a binary one, and it is not dependent on other algorithms such as RPIC detectors to segment the ECG. Also, since congestive heart failure is a chronic condition, we conducted an extensive study to assess the best duration of the temporal window in which to observe the pathology. This was done within two scenarios, the inter and intra patients. Therefore, this study is steered by the following research questions. RQ1, what is the optimal value of the length parameter W? With this research question, we aim to tune this length parameter to understand how many seconds of observation are needed to perform the best prediction. With the second research question, we asked, what is the classification effectiveness of Harper? With this second research question, we wanted to evaluate the accuracy of Harper in the detection of congestive heart failure episode in the context of the scientific literature. We also wanted to evaluate Harper in two different validation techniques, such as the intrapatient and the interpatient strategies. So we are going to present Harper. So the high-level workflow of Harper is described in the slide. First, we consider the length of an observation window in seconds. Then, Harper takes the ECG signal from the patient as input, having a length greater than or equal to W. Next, the ECG signal is divided into several segments based on the segmentation window. On each segment, we performed a feature extraction step. Finally, the extracted features are submitted to a trained machine learning model which performs the signal classification. In this way, as the output of the last step, Harper provides a label for the most probable classification among normal sinus rhythm, congestive heart failure, and ARRR, which means no congestive heart failure, but an arrhythmia pathological condition. Well, let's now focus on the steps between the buffered signal and the generation of the feature vector. The signal processing performed on the ECG starts with the detrend operation, where the average of the signal is computed and subtracted from the input signal. Then the following literature features are extracted: the energy of maximal overlap discrete wavelet transform, the autoregressive model, the multifractal wavelet leader, and the fast Fourier transform. We involve this feature because successfully experimented in other studies. So we are going to introduce now the experimental procedure. So we used a dataset of 162 ECG recordings extracted from the Physionet database provided by MathWorks. In the final dataset, there are 36 patients with normal sinus rhythm, 96 with no congestive heart failure anomalous episodes, for example arrhythmia, and 30 recordings from subjects affected by congestive heart failure. The reason behind the use of this dataset is that it is composed of signals from different datasets, providing a more heterogeneous set of ECG recordings, and that it contains not only congestive heart failure recordings, but also the no CHF class. For the first research question, we first defined a set of possible duration of time windows. Furthermore, we performed ECG segmentation according to these windows. After we applied a technique of synthetic sampling, pre-processing on the feature, which consists of standardization, and after a validation scheme compliant with the intra-patient scenario, which consists in an division of the dataset in testing and train according to the 80-20 percentage of random splitting. The final last step is dedicated to the classification. Then we opted for using the best model obtained from the intra-patient scenario to assess the best window duration, also in the inter-patient scenario. The pre-processing scheme used was the same. What changes here is the validation strategy, which is a leave one subject out. With respect to the second research question, taking into account the result of the first research question and to assess the classification performances of Harper, we conduct its validation considering the best ECG time window combining with the best performing machine learning classification pipeline. Moreover, we compared our approach with a selected baseline to assess if Harper has comparable performance to a state-of-the-art approach for congestive heart failure detection. So let's analyze the results. So the primary outcome of this experimentation is that an observation of 25 seconds allowed to obtain the best overall metrics with a pipeline composed of only a random forest model. In this case, the result exceeded 0.99 on all the evaluated classification metrics, which are the sensitivity, specificity, precision, and F1 score. In this figure, the box plots of the classification metric are obtained by experimenting with each time window. In particular, from this distribution of data, it is possible to derive how the time observation with the highest median of the classification performance is at 25 seconds. However, the 20 and 25 time windows are the best in terms of robustness because even the outliers are approximately above 0.96. Following the same procedure, the result of the intra-patient validation protocol showed that in this specific condition, the best time window is defined by 60 seconds and not 25 as previously obtained in the other scenario. The reason behind this could be that in the case of the patient that is never examined before, a larger time window is needed to achieve an accurate classification. Well, on the right side, there are the results of the inter-patient validation, where the baseline approach slightly outperforms Harper for a few percentage points. This could be due to their perfectly balanced dataset. For the intra-patient validation on the left side, Harper outperforms the baseline on both the normal sinus rhythm and congestive heart failure classes. Mainly, for the congestive heart failure class, we have a better sensitivity and specificity values, but a lower precision value. This means that our approach has more false positive than the baseline. According to us, this could be an acceptable trade-off in the scenario of online monitoring and detection. So we have presented Harper, a detector of congestive heart failure to be embedded in the decision support system of the Atticus telemedicine project. The result of this work clearly highlights that a longer observation of the ECG is needed to best detect congestive heart failure episodes when monitoring in real time a new user of an Internet of Medical Things system. The duration can be then reduced once enough data points are made available to the machine learning model. Harper is highly accurate and it showed great potential to be embedded in scenario of continuous monitoring due to its high accuracy in detection and technological independence. Indeed, no other algorithms are needed to obtain the ECG segmentation. Thank you all for your kind attention.